Welcome to the lesson, Fuel System. The RJ stores its fuel in 3 tank areas: wing tanks left and right, center tank, auxiliary tanks, also known as pannier tanks, to increase the fuel capacity if required by the customer. Fuel is transferred from the center and then the auxiliaries to the wing tanks, and from there to the feed tanks. All fuel burned by the engines has to pass through feed tanks. Under normal conditions, fuel is moved by jet pumps from the main fuel tanks to the feed tanks. Each feed tank has an electric boost pump to supply its own engine and to power the jet pumps. A single boost pump is capable of supplying all engines if the other boost pumps fail. If all boost pumps fail, the jet pumps are powered by hydraulic fuel pumps and the engines will suck fuel from the feed tanks. If the hydraulic pumps also fail, most fuel can still be fed to the engines by a combination of gravity feed and suction. Fuel is pumped to each engine by its own AC-powered boost pump, through a non-return valve and a low-pressure valve. The left outer and right inner pumps are powered by AC1. The left inner and right outer pumps are powered by AC2. In an emergency, closure of the low-pressure valve is carried out mechanically by operation of the fire handle. The boost pumps are located in feed tanks in the outer part of each wing. The outer wing is used because it is the lowest part of the system and therefore the point to which fuel naturally flows under gravity. The inner feed tank supplies the inner engine. The left inner feed tank also supplies the fuel for the APU. The outer feed tank supplies the outer engine. Overflow from the inner feed tank maintains the outer feed tank full via a high-level weir or spillway. For this overflow to occur, the transfer system to the inner feed tank must be capable of exceeding the maximum demand from the engines. Outboard of the outer feed tank is a vent or surge tank that takes excess fuel in the event of overfilling due to thermal expansion. The tank is vented to atmosphere via a stack pipe in the tank to an outlet under each wing called a NACA duct. Any fuel remaining in the surge tank will be sucked back into the wing tank as the wing tank fuel is used. The design of a NACA duct creates a positive pressure. This makes it resistant to icing and allows the pressure to be felt in the fuel tanks. This aids gravity and suction feed in the event of loss of boost pumps. The boost pumps in the feed tanks also power associated jet pumps that transfer fuel. The inner jet pumps are necessary because at lower fuel states, gravity feed alone is insufficient to keep the feed tanks full at maximum demand from the engines. Three jet pumps in the inner feed tank transfer fuel from the main wing compartments. A fourth jet pump transfers fuel from within the feed tank to the boost pump compartment. More than one is necessary to ensure that supply exceeds demand, particularly when one boost pump is supplying all engines. 2 jet pumps in the outer feed tank are necessary at low fuel states to transfer fuel from the lower parts of the tank to the boost pump compartments. A jet pump powered by the inner boost pump transfers fuel from the center tank to its wing tank. If transfer fails on one side, the remaining jet pump will transfer fuel to its wing tank except for 180 kilograms, 390 pounds, which will be unusable. Fuel reserve will now need to be increased by the 180 kilograms or 390 pounds that is now trapped. Transfer is controlled by the center tank switch on the fuel panel. When the center tank transfer switch has been selected to auto, weight on wheels switches allow the fuel to transfer automatically when the aircraft takes off. Unlike the other tanks, transfer from the auxiliary tanks is by gravity feed, except for the last 95 kilograms or 209 pounds. Gravity feed will commence when center tank transfer is complete and the falling wing tank level uncovers the connecting vent line. The final 95 kilograms or 209 pounds are transferred by another jet pump powered by the inner boost pump. Any boost pump is capable of supplying all 4 engines and the center tank transfer jet pumps. An adjacent engine is supplied through a common feed valve. Engines on the other side can be fed through the crossfeed valve to the inner engine, and then common feed to the outer engine. If all the boost pumps fail due to a loss of engine and APU generators, 2 yellow hydraulic system standby pumps will automatically power the 4 jet pumps topping up the inner feed tank. The engine-driven fuel pumps will then suck fuel to the engine through the normal line. Although transfer from the center tank will be lost, the auxiliary tanks will transfer by gravity only. If the standby pumps also fail, fuel will still gravity feed to the inner feed tanks through flap valves. Fuel will then spill from the inner to the outer feed tank and the engines will suction feed. Gravity flow will keep the feed tanks full until about 2,000 kilograms or 4,400 pounds per side. From that point, the inner feed tank quantity will fall in line with the main wing tank, leading to isolation of the outer feed tank. This would eventually lead to flameout of the outer engine. Fuel state can be checked and refueling carried out provided batteries are fitted. They do not need to be switched on. The fuel state can be checked by pressing and holding the fuel quantity push button on the flight deck. In the event of a fuel gauge failure, magnetic level indicators, MLIs, are used to check the fuel when the aircraft is on the ground. Each wing has 2 MLIs, one inboard for high fuel states and one outboard for lower fuel states. 2 are required because the wing slopes down toward the tip and headroll. If using an MLI, the aircraft's attitude must be noted as this directly affects the fuel quantity registered. There is an inclinometer in the right-hand main landing gear bay that gives information required to work out the correct fuel quantities. This procedure is given in the MOM, Volume 1. With auxiliary tanks and full fuel load selected, the indications will be the following. Indications without auxiliary tanks. In flight, the asymmetry imbalance of the fuel in the wings must not exceed 680 kilograms or 1,500 pounds. If the center tank fails to transfer fuel to one wing tank, 180 kilograms or 390 pounds of unusable fuel will be left in the center tank. Loss of the boost pumps causes loss of the auxiliary tank transfer jet pump. In this case, however, transfer is by gravity feed until a final 95 kilograms or 209 pounds in each tank, which is unusable. Outside the aircraft, it is important to check the water drains, 5 on each wing, and surge tank vents are unblocked. There are no leaks from the fuel panels, 10 on each wing. Magnetic level indicators, MLIs, are secure. There are 2 on each wing. The refueling panel here. Before refueling commences, the earth-ground bonding must be connected. When refuel panel door is open or the master switch is on, the amber refuel selected light illuminates on the flight deck. During refueling, the crossfeed should be shut, and all fuel pumps should be switched off. The left inner fuel pump may be left on when the APU is in use. Use of the right inner fuel pump would lead to overfueling of the right wing and spillage from the NACA duct. Attaching the tanker's hose to the refuel coupling starts the refueling procedure. Pressure refueling is carried out at the single-point refuel panel. DC power for refueling is given when the master switch is selected on at the refueling panel. The total fuel quantity required is dialed up on the pre-selector.